Hey, what's up, YouTube? We're finally back with episode 2. I'm so excited to share this with you all today. Wow, I just cannot believe the reception so far to episode 0 and 1. Y'all, that was my first ever proper lecture. My first ever proper lecture has hit something like 30,000 views so far, and my announcement that I'm going to lecture has hit like over 150,000. So that's insane. I am so honored by all of the kind comments and everything so far. So thank you for being here. It's hard. It's a very hard act to follow. So I've been trying to treat it with the respect that I feel it deserves. Uh, so let's see. Today is July 15th. I've tried this a few times. I had one vision of it, completely threw that away. Had another vision for it, completely threw that away. And then this morning I was like, you know what? Let's do this. And I think that this is I think I'm happy with where it lands, and I would love feedback after the video. So thank you for watching. This is an intro to pure mathematics, proof-based mathematics. But what is beautiful about this book to me is that it is familiar mathematics as well. It is not a number theory book. It is not an abstract algebra book. This is like new types of mathematics. Those books are new mathematics with an introduction to proofs. So I think that this gives us an opportunity that seems to be resonating for a lot of people, for adults who want to come back and relearn math the second time around and to learn math better or something. And I really just think that this so far is an excellent book for that. So let's keep going. We're going to do one. I think that this will be the last episode on sections 1 and 2 of Lang. And then next time we'll move on to section 3. So hope you enjoy. First, let's start out with some frequently asked questions. First, where's episode 2? So I already said that there were a couple of scrapped attempts. Yeah, and here it is. I guess here it is. The thing about this is that, well, yeah, there's two different directions I want to take that thought. But first off, here's episode 2. Let me explain to you all, and this is very related to the next related question. Should you all watch the live streams? Where's episode 2? What's going on? I'm confused. Where's the rest? I'm shooting for one episode a week. I think I can do one episode a week and hit the quality bar that I'm looking for myself. But I'm actually going to shoot for 2. Like, I'm gonna aim for 2 and commit to 1. Like, so as of today, we're 1 day late, and that's okay. That's just okay. It's gonna be fine. So apologies for how long it's taken to answer. Yes and no. You can watch the live streams if you want to. It's just totally unstructured, unplanned. It's more like a giant office hours kind of, or problem solving session. So Luna. So you're welcome to watch the live streams. I mean, they're mostly there for those who are there live to be able to ask questions and just hang out and just meet fellow math enthusiasts. So if I'm live, like, please stop by, say hi. It means the world to me to meet all the people who are enjoying the stuff that I do. So thank you. The VODs, I do not recommend. Like, that is not the course, and I feel bad that it's taken so long to answer that, because that is not the course. You're not supposed to go and watch 120 something days of unstructured 3-hour, 3 hour practice sessions. So no, don't worry. Yeah, you can keep an eye out for these blue thumbnails. All right, next question. What about the course? So speaking of course, what about the course? Can I join the course? please keep emailing me. Please keep emailing me. I don't know how I'm going to solve this problem. It's a great problem to have, but there's so many people who want to study math with me, and that makes me want to cry. Dude, that's amazing. Thank you. Keep emailing me, jcpractices@gmail.com, and we will figure something out. My vision for the course is a small, tight-knit group of 10 people, private, not recorded, and I want a diverse and amazing little group of people. Some people who are learning math for the first time or advanced math for the first time. Some people who are coming back to math who were, mediocre in school or terrible in school and they want to come back later in retirement. I feel that this is the structure that I want to build, and it's going to most closely match my ultimate goal of being a teacher and leading a classroom, like leading and running a classroom and a small discussion session. So keep emailing me and we'll figure something out. We might have to randomize it or something. We'll figure something out. So who is this for? I think that I've alluded to that for a second here. Well, it's easy to say everyone. It's really easy to just say everyone. But I think that's a cop out. I don't like it when somebody answers like, yes, both, or like the answer is yes, or everyone, like all of the above. No, you have to prioritize. So first, jobs. The first person that this is for me. I'm practicing. I want to learn how to teach mathematics and run a live lecture. This is all live. It's an unedited take. I feel that that's very important for me, and this is practice for me. So I was expecting that nobody was going to watch these videos. Luna, okay. This is another frequently asked question. People asked if the cat can go, and she's not going to go. I'm sorry. I'm very sorry, because we're just going to have to filter some people out because she's so cute, and I love her too much. And she runs this household. So welcome, Luna. All right, who is this for? It's for me. Then, secondly, this is for adults. I think that we have a real opportunity here that seems to be resonating for people. If you just go read those comments in the first video, especially, man, thank you. Like, the fact that I'm reaching some people who were terrible at math and have math trauma, like literally math trauma, and some people are trying. Like maybe somebody said maybe you'll be the one to convince me to be interested in math or to help them with math. Like, dude, that's such a high responsibility. So thank you. Okay, so in a tiebreaker, I'm going to make decisions for me. In a tiebreaker, I'm going to make decisions for adults over kids. So this is also for kids. This is also for middle schoolers. I've said multiple times that I want to run a middle school classroom. I just had my interview yesterday, and I'm happy with how it went. That's all I can hope for. I'm sure that the other candidate is fully qualified and much more qualified in a lot of ways versus me. But dude, like I just like working with people in person. Anyways, I guess that's more point one, but yes, I do want this to be accessible even to high schoolers. I would say who is this not for is kind of a better question on something like this. Like when you ask like, who is this for? Everyone like, okay, wait a minute. Who is this not for? I still think it's for college students. I still think it's for math people who already know this material. I do think I want it to still be enjoyable for everyone. But the least important person to me, I guess, is going to be people who already know math or they're not that, I don't know. Yeah. I'm putting a negative spin on this for a second, but I guess what I'm trying to say is if you want to learn intro to proofs and you're a college student, if you're like a math major, this course is just going to be moving very slowly for you because it might take me a while to upload a lesson. We're also learning high school mathematics, not abstract algebra, not yet. So I'd say that that's the one target audience or the one audience. If you want to learn abstract algebra, this just probably isn't the best material for you. But if you're here for the vibes and you want to just throw it on and listen to it because you like hearing somebody who just is geeking out so much and you like this cute cat, she's so cute, then, you're welcome here as well if you're here for the vibes. All right, now, another question. This is just one of the top questions. How should I continue working through this? Should I get the book or should I watch the lectures? Both. I mean, you need to, I'm here to metaphorically and literally add color to Lang's book. I'm not here to replace Lang's book, and I'm certainly not here, you're not going to learn mathematics by just watching any lectures or videos or in person or online. There's a saying that math is not a spectator sport, and it really is true. You need to get your hands dirty with exercises. So I'm going to structure today's lecture with an exercises first lens, and we will be beginning with some exercises. So yeah, how should I work this? Jump around. You don't have to wait for me. And we're not in, we're adults here. We're adults now studying math as adults. I'm going to be really random. You're not going to be able to predict at times which section I do next. Just jump around, look at the table of contents of this book. And if there's a topic that you're curious about, jump right to the exercises and try to work those. And if you get stuck on those exercises, read the section and then try the exercises again. And if you get bored of that topic, look at another topic. This book is all of familiar middle school, high school, secondary level math. I like the term pre-college. I think that this is pre-college math. All right, so exercises. So let's begin. I'm going to try to pick an exercise from Lang and we'll work it. For those who are not familiar with this notation, this is exercise 1 from section 1.1. I really like that, squiggly symbol, for sections. All right, so exercise 1 from section 1.1 from Lang. He just didn't, which is a shame. I think that's a shame, dude. There's beautiful questions, there's beautiful exercises that you can make out of the material from section 1. If anything, I think he moves just a little too fast for my taste, but I'm very pure math pilled, right? I love number theory. I love the positive integers. He moves very quickly. Page 5, counting numbers. Page 6, integers. In other words, positive numbers and then negative numbers. I would chill. I want to chill for a moment longer on positive numbers because there's really, really nice questions and exercises that you can do just with the positive numbers. Look at this cute cat. She's so happy. She doesn't understand math, but she's here for the vibes. She's here for the vibes. All right, so exercise 1. The Fibonacci numbers, man. Just again and again, we're going to see them again and again. So I love introducing a concept, working it as an exercise, coming back to that same concept again later and doing it in more depth. So we're going to see this one again and again. But first, dude, I want to give a special shout out to somebody who left a comment in a recent calculus stream. I was working the sequence of the harmonic series, and because somebody asked, how would I introduce somebody to calculus if you've never seen calculus before? So we started adding the reciprocal numbers, and then we started adding the reciprocal squares. But they commented, hey, I'm a shopkeeper and I've in my life always had trouble adding numbers. Like at this point, even just single digit additions are hard for me. And I just like, man, there's so many people out there who just failed this person. Like I hate how math education in the US, I've only lived in the US, goes level 0, level 1, level 2, level 3, and we pretend as if math is this linear progression. And like if you're in level 3, level 4, and you still are struggling about level 0 or 1, like, haha, sucks to be you. You better catch up somehow on your own. Like, you better get a private tutor or, go to your teacher's office hours or something. And then some kids will just like decide that they're not math people and that they can't catch up. So this one is for you, dude, the person in the calculus stream. Thank you for watching and for joining this community and for trying to better yourself. I think that this is pure math. This is pure math. This is arithmetic. Addition of numbers and practicing addition of numbers is pure math. This is an excellent book for anybody out there who wants to improve their mental math. It's a tiny little book. I mean, it's from the Dover Company, which is just, such a great publishing house. Like, it's just math. Like, it is just a bunch of really cool mental math and, quick speed ups in arithmetic exercises. Like, really like this one. But before we even need that, like I use this literally with students. I tutor little kids, not middle schoolers, but like younger. And I just like to introduce addition with these things, man. Like, all right, we don't have to get scary with formalism of definitions. I just write down 1, 1, and I ask the student, what is 1 plus 1? And then they say 2. And then I say, what about 2 plus 1? And they say 3. And then I say, what about 3 plus 2? And they say 5. And then I say, what about 5 plus 3? 8. What about 8 plus 5? 13. What about 13 plus 8? 21. At some point, these are going to start getting harder for anybody. Man, like at some point, whoever you are, this is going to get difficult, especially if you're trying to do it in your head. And I love these types of exercises that are just normalizing. Like everybody can have fun putting away TikTok for literally 5 minutes. Set a 5-minute timer, put away TikTok, and for the next 5 minutes, when your coworker is running late to a meeting or something, just run the Fibonacci numbers, man. Like it's not the worst way to spend 5 minutes. So you can keep going. 34 plus 21, 55, 55 plus 34, 89, 89 plus 55. This is the first one where I just want to show one mental math trick. 89, you can compare, and you can think of 89 as 100 minus 11. Adding 100 to a number is fairly easy. So 55, 155 minus 11 is 144. So that's an example of the kind of tricks. Oops, 144. There it is. That's just one example of the kind of tricks that you can learn if you pick up that book. I don't even have affiliate links because I'm too lazy to do it. And someday I will. So if you're watching this video in the future, check out the description. And maybe I've set up affiliate links by then. I want these books to sell out because there's so many people studying math because it's just fun. Adding numbers is fun, dude. Like there are no roller coasters. You're not adding marbles and elephants and roller coasters together in this book. It is just math. This is a pure math book for kindergartners. Like it is, I mean, it's a little hard for kindergartners, but it is that type of math. But, there's just, I mean, it's a great book. I think it's really beautiful. Okay. So, I've seen it firsthand that students just geek out about this so much more. So I've done it for the first time recently, like truly, you know, do as I say, not as I do, or something. I've done it recently, and in 5 minutes, I got to 28,657. Leave a comment in the comment section. How far did you get? I might be able to do faster, maybe not. I'm proud of this one way or another because I got there. I got there without any scratch work at all, and so that's one variant of this game that you can play for yourself. No scratch work. And then I tried again. There's another approach that also works. There's another approach, and I found a speed up, and I got to 3,524,578. And I was very proud about that one because for a long time with this speed up, I was stuck here. And if you're curious about how it took me 3 times and I kept hitting 1,597. And then on the 4th time, I got to 3.5 million, whatever. So we'll talk about that in the future video. Yeah. All right. Next, another exercise for just adding numbers because this is another excellent exercise and we may come back to it again and again. We will come back to this one for sure. Partitions. So last time we saw these partitions of the number 5. That's a little off screen, isn't it? So I wrote this out last time, and we found that there are exactly 7 partitions of the number 5. And these are all of them. This is kind of nice. Like, assuming commutativity, so 3 plus 2 is the same thing as 2 plus 3, so we may as well organize it. I love to alphabetize everything I can. I love to lexicographically sort, so these are all just descending sorting, like biggest numbers left to the left, smallest numbers to the right. And then there's a unique 7 ways to split up a thing like 5 apples or something. So do the same thing for yourself. Do the same exercise for 6 and tell me how many there are. All right. Rules for addition. Show that negative of a plus b plus c is the same as negative a plus negative b plus negative c. I think that we're running a little behind on time for this video, unfortunately. So I kind of want to move on and hit the rest of this talk. But I'm going to give you the first step on this. And I want you to read Lang. Like this, these don't replace reading the book. So I'm going to give you the first step. First, and just write sentences. Yeah, write sentences. First, we recall the definition of a negative number. So Lang doesn't go this far to say that this is the definition. He uses the analogy that we've all seen looking at a number line. You have a ruler that goes this direction and it has 12 inches, and then you can glue another ruler in the other direction, and now we say that we have the numbers negative 12 to positive 12. Then we just imagine we have an infinite ruler that goes in both directions. That's a very good intuitive description. I want to offer... Well, first, here. Let's just write down this definition. For any number, let's say n, it's very conventional to use the letter n for a whole number. N plus negative n equals 0. Okay. I know that this sounds like a weird shower thought, but negative numbers don't exist. They're imaginary. Negative numbers we've imagined to exist. Positive numbers, for that matter, also don't exist. They are also an imagination. That they are also an abstraction of something that we've observed in the physical world. And I like to imagine thinking just way back to our grand ancestors. uh, it seems obvious in retrospect, like the idea of a number, but that was not obvious. I wonder how long in humankind, in human history, how long did it take until somebody came up with the idea of a number? I am going to argue that the closest thing to numbers existing in the real world are these, dude. These are the closest thing to numbers actually physically existing in the real world. These are so useful. Like, if somebody else has gathered some food, and somebody else has gathered some food, and you want to understand if you have enough food to survive, you can just look at it and think, yeah, probably. And then it's a coin flip, and at some point your guesses are good enough that you tend to survive. But then at some point somebody was probably like, okay, wait a minute. I see a lot of apples there. That person, oh wait, I'm trying to understand how many apples they have. There's one, there's two, there's three. Whoa, dude. And then they just show this to everybody nearby, and it just catches on, and it's a viral idea that just was immediately successful. These are so useful. It's why I think as little kids we learn to finger count. It's because these are the numbers, I think. So then here are our numbers. We need to invent zero, though. Like, okay, well, if they didn't have food, I guess I don't lift any fingers, right? Okay, so if they gathered five apples and they gathered 0 pieces of meat, I guess we have five pieces of food today. Then we can make an argument that A plus B is the same as B plus A, right? That we have commutativity. Associativity, maybe you're counting multiple things on one hand, like you're just continuing to count. Like instead of doing 2 apples and 3 pieces of meat, you can go 1, 2, 3, 4, 5. I don't know. I think that there's something to this analogy, but what I want to emphasize here is that math is built on these abstract definitions. It's a different abstract world. These ideas don't physically exist, but they're inventions that we've made, and we just discover all these beautiful properties about the numbers. So what's a negative number then? I guess it's reducing your fingers, like, dropping the fingers. That action of letting go of a finger is probably a negative number then in this analogy. But now we want to formalize that and be able to write it down somewhere, carve it into the walls or something. So this is going to be the beginning. So your goal is, therefore, and goal is a technical word in math nowadays. Your goal is to show that A plus B plus C, that the additive inverse of that, which is there, is this thing. So you do that first, plus this one has double parentheses, but that's okay. I guess we pretty much completed this. It's almost done. There's your hint. You want to show that this left-hand side eventually equals the right-hand side being 0. And then therefore that will show that that the right-hand side is the additive inverse. It's the negative version of A plus B plus C. Okay, let's keep going. So let's look again at the integers and natural numbers. And I've already kind of referred to some of these things. I showed N1, the definition of zero. I've referred to that. And then this fact was N2. And this was what I used right here. So this is N2. Lang, as you read Lang, you'll see that he boxes these mathematical facts. And he doesn't yet make a distinction, but these two he takes as assumptions or definitions. There are different types of mathematical facts. Some of them are definitions that we invent, and then other ones are results or theorems or examples or corollaries. There's like kind of a zoo of different names for them. I just call them all math facts. So these are our first two math facts. We'll take these two as definitions and assumptions, and then we get some examples. The examples are not that interesting right now, so let's move on. They're kind of what you'd expect, I feel. And my example of the Fibonacci numbers is, I think it belongs as an exercise there. All right. We've already seen commutativity and associativity in the last lecture. Now we come across our first ever proof. If A plus B is equal to 0, then B is negative A and A is negative B. This one's not true. I forgot to update that, didn't I? I just noticed earlier. I think I'm lying to you. It was something else. There was another one where I felt like, yeah, dang. Oh well, I messed this up. Yeah, I remember now. So there were some mathematical facts, and this, too bad. Oh well. I should have done this here. Oh well, that's fine. I got this wrong. So these are mathematical facts. How do we prove these? We don't. We actually just don't. We take these as assumptions and, or definitions. To just expand on that just a tiny bit more, I know I can yap. I studied philosophy as well as math, so I'm professionally trained in yapping. These are the mathematical worlds that we will be seeing in this book, and I like to write it because it looks really cool. So I don't think I've done this yet in this series or in these episodes. Where's a nice blank space? Right here. Okay. So these are our mathematical worlds that we're going to live in. And what I just argued for is that you can spend a lot of there are a lot of interesting questions that you can ask just about the positive numbers. But then Lang moves pretty quick to the positive and negative integers. And then these things are the fractions. These things are the real numbers. And then these things are the complex numbers. So the fractions include 1/2. The real numbers include square root of 2 or pi. And then the complex numbers include the square root of -1, which just doesn't exist. Or it's just another imagination. I like to show this. With the complex numbers, I know that this is kind of a brief detour, but this is truly, this is primarily meant for people revisiting this math and doing it in more depth, right? We may or may not remember that this is the graph of x squared plus 1, right? It never equals 0. It never crosses the x-axis, right? It doesn't intersect. Let's just imagine it did. Let's just imagine it does cross the x-axis somehow. Then we build a really incredibly cool field of math that literally a beautiful field of math that just makes a lot of things that felt incomplete now feel very complete in the complex numbers. Let's move on. So the proof of this one, I think, is going to be similar to what I've already sketched out. You can read Lang on this, but pause these videos and try them yourself at times. All right, so next facts that we're going to take are these two. A is the negative of negative A. Like if you multiply two negatives, you get a positive. That's like a phrase that we say all the time, but we never see the reason why. We rarely prove it. And we did, if we do, like I had excellent teachers. I never saw proof-based mathematics, but I know I saw mathematical arguments from them just hit it. I wish that they would just write the word proof and do their, not completely precise way of proving something. But you can do this for yourself. I really do believe that if you have followed these other ones and you crack open Lang, you can understand that proof, and it is given to you. And similarly on this one, I want you to try it and then compare your solution to Lang's solution. Highly recommend getting a paper copy. I love crossing out exercises, just like a right there through each of the numbers. It just feels great, and it literally feels great going to a cafe, leaving your phone at home because it's blowing up with notifications from TikTok or something, and just go to a cafe, get a strong cup of coffee, and study some math. It's so delightful on paper. I know I sound like an old man or a hypocrite or something, but there are advantages to digital and there are advantages to paper. When I'm really truly trying to engage with math and I want focus, I want a blank piece of paper where my pencil is scratchy. It feels scratchy and you get muscle memory in it. All right, now, now we get a couple of examples here. If A and B are positive integers, then A plus B, I want you to pause and think about what this fact would be. A plus B is also a positive integer. Okay? That seems so obvious. That seems so duh. That even Lang says, this is obvious. It's kind of hard to think that it's not. I would say that you could argue that you define addition in the natural numbers first. And then you have addition, and you define addition in a way that the addition of two natural numbers is another natural number, and then you extend it to the integers. So this fact is true just from the natural numbers. It's not possible that adding two natural numbers will give you a negative number because addition is well defined on the natural numbers. Let's keep moving. So now another example. If A and B are negative integers, then A plus B is negative. That one, now Lang gives an argument for this one, and I think that's awesome. Like, these are just patterns that we learn and memorize intuitively, and I don't know if it's right to try to give a proof to a little kid learning this for the first time, but we never go back and revisit it until you're in college for a lot of people. And I think that we should revisit this basic mathematics in middle school or high school and do it again and do it in more depth. More mathematical maturity is a word. Again, I want you to read his proof and I want you to try it yourself first. Next example, if A plus B is C, then A is C minus B, and there's a proof. So now we're getting to these general mathematical tricks. We learn these types of equations all the time, or we work with those, and how can I move B to the other side and change the sign? I think you can imagine the proof, and You can try it yourself and then compare to how Lang precisely wrote it. Like the wording matters very much in proofs. Similarly, we can subtract a from both sides of the equation. Next, for example, and I want to give this an entire page right now, because once you've built all that theory so far, if you understand the general generalizations that we've seen so far, doesn't matter what numbers we're working with, A, B, and C, this will be a fact for all eternity in any universe. In any universe where logic applies, and it would be very hard to imagine a universe without logic. If x plus 3 equals 5 in any universe, then x is 5 minus 3 is 2. This is the beginning of algebra. This is like, or pre-algebra, or I don't know. It's just math. It's just math. But the abstraction of solving these equations is something that we learn patterns around, but now this is an application of this fact that we know will always be true. So once again, this sentence is in this form. A plus B equals C. Therefore, I can subtract B from both sides of the equation. I can subtract B from both sides of this equation to get A is C minus B, and now this is exactly the form here, but now we have specific numbers 5 and 3, so we can actually subtract those two. So there's my best attempt at trying to show you all that pure mathematics, rigorous proof-based mathematics, we do not solve these types of equations that often. There are examples, but they're more to illustrate examples, like specific places where some general theory works. You prove the general theory, and then you apply that theory to specific cases. This is kind of like applied math in a sense. Like we applied, that's not really fair at all. That's not true. That's not true. But like applied math is never mind. I'm just going to move on. I'm going to get some hate at some point in the comments, I feel. But I hope you all know what I mean. This is an application of the theory that we've built. And if you look at Lang's exercise sets, he's a very careful guy. He thinks very deeply about presentation style in general. And in the exercise set, there's like 13 or something scary looking hieroglyphics that look like this. And they're generalities, and you're working with abstraction. And then like the next, oops, sorry, that might be loud on the microphone. And then the next 8 or so are just like really simple, like -2 plus x is 4. Like the next 8 are all like this. And it feels like these are just so simple compared to the previous ones, but it's because these are simpler. Like once you understand the reason why we can solve these equations this way, then none of these are surprising. None of these should be hard. Like I think if you do the work to understand the concepts, then the specific instances are clear and there's no mystery. And that's beautiful. That is beautiful. That's where math can make sense, I hope, for some people. So I moved pretty quickly through these, and I don't know for the people who would struggle with solving an equation like this if I really helped. But if you try to read the book and work through it, we're doing things like really. I should just prove one of these. yeah, we had this one. If A plus B is C, then um, which one are we solving for? Oh yeah, then A plus B, we can consider this uh, this equality. Um, since A plus B is the same as C, then adding negative B to itself should preserve the same value, right? Then using the associative law, using associativity, we can regroup those parentheses. And this equals C plus negative B. I'm going to go ahead and rewrite. No, let's do this. In pure math, you care a lot about the presentation of a proof, I think. Even though I could have done it in one line, I like to use like these double struck arrows in order to say if this equality is true, if this line is true, then this next line is true, then this next line is true. We've seen that the definition of subtraction is adding a negative number. That's just another way to write it. That's just another symbol to do it. And then subtracting a number from itself is 0. And then, therefore, A equals C minus B. I think that you should do these, you should do a handful of these, and that's why he's given them as exercises. You really should do a handful of these, and once you've done them, as I said, if you've done all 13, then the next ones are just going to seem really, really easy, or just uninteresting. Thank you. Dude, thank you so much, everybody. I've already said it earlier, but thank you so much. Ways that you can help me out and just, this is all a gratitude practice. Thank you, everybody, so much. I want to be putting this stuff out there for free. It makes me very happy to share my passion. If you want to extend some gratitude back, here are some ways. Just leave a comment and just say thanks. Like, it could just literally be the one word thanks, or any kind of feedback. Like, feedback is a gift, dude. Like, I love feedback. So comment section is great. Like, anything I could do better, anything that you think would have been better. If you really don't like Luna because she's distracting, I appreciate that feedback very much. If you think that this could have been faster, etc. Feedback.jcpractices, that's just a Google form, and you can either be anonymous or include your name or contact info. So thank you. I also do have a buy me a coffee. So if anybody really likes what I'm doing, that's an option, but just absolutely never expected, obviously. Thank you. I'm really happy with how this episode 2 turned out, and I hope you enjoyed it too. Thank you. Take care. Bye.